And the following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. When you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I will respond as soon as I can. Well, today, if there's any questions, we'll answer. And then after that, we're going to go on to section 11.3. Are there any questions from yesterday?
No, I don't have any.
Diana, how about you?
No, I did not.
Did you get your calculator question answered? Did you figure it out?
No, I didn't, but I mean, it's like I said, it's livable, but I don't know.
Yeah, because I talked to several colleagues.
I just turned it on and it works.
Normally?
Yeah.
Huh.
And you know what I think it is? So
What?
my son plays with my calculator. And he's always pressing the numbers. And for some reason right now, when I turned it on, it doesn't have the bottom where it said FIX, fix.
Yeah.
Now it just says DEG. So I'm guessing he pressed the right button now.
So if it's working, hide it from your son.
Yeah, it's because he loves numbers. So
yeah.
Now I know. Lesson
Okay.
learned. But okay, thank you.
Yeah, because the people I called had the same problem I did without having one in front of them. They had the same theory I did. So, but
yeah, no worries. That's
anyway,
fine. Thank you.
I should have just consulted your son. Okay.
Thank you.
So then we're going to go on and take a look at section 11.3 today. And now I'm going to do something extremely dangerous because recall the other day when I switched over to the graphing screen, how well things did not go. So hopefully I'll have better luck today. We're going to find out. I tested it earlier this morning and it worked, but we'll see if it still works. Okay. So there, and there. We have looked at and talked about linear equations. An example might be y equals 2x, the graph of which would be a straight line. And that's not accurate, but you get the idea. We've looked at quadratic or second degree equations like y equals x squared, the graph of which is a parabola. Now we're going to look at equations that are called exponential equations. And what they look like is this: y equals 2 raised to the x power. So here's an example. Notice that the variable is not the base, the variable is the exponent. So let's just make a table here. I'm going to make a table with some values and we'll talk about that, see what's going to happen here. As I think I've mentioned before, whenever I'm exploring a new equation, I always like to start with from -3 to +3 and then see where to go from there. Now, if x is -3, y would equal 2 to the -3 power. It's so nice to be able to write a 3 after yesterday. Okay, of course, I still didn't do a very good job of it. But 2 to the -3 power would be 1 over 2 raised to the +3 power, right? Are you okay with that? Remember that rule?
Yes.
Okay, which would be 1 over 8. If x is -2, y equals 2 to the -2 power, which is 1 over 2 to the 2 power, which is 1/4. If x is -1, y equals 2 to the -1 power, which is 1 over 2 to the +1 power, or 1/2. If x is 0, what's 2 to the 0 power?
0.
No. Something raised to the 0 power other than 0 to the 0 power is?
Undefined.
No, it's 1.
Oh.
Dividing by 0 is undefined, but this is the number 1, okay? Do we need to review that some more, or are you okay with that?
As long as we give another example like later on, I think
Yeah.
should be okay.
Okay, all right. If x is 1, y equals 2 to the 1 power, which is 2. If x is 2, y equals 2 squared, which is 4. And if x is 3, 2 to the 3 power is 8. Okay. Now, unlike quadratic or second degree equations, where if we look at the table for the parabolas, we have two different x values going to the same y value. Here we've got sort of a reciprocal situation going on. You see that? Okay. Now, if we plot those points, when x is -3, y is 1/8. When x is -2, y is 1/4. When x is -1, y is 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is 8. So we get this graph that looks like this. Now, as x keeps increasing, can you see that y is going to keep increasing, getting larger and larger? What about going the other direction? What about -4, -5, -6? Well, -4 would be what? 1/16, and then -5 would be 1/32, 1/64. So what I'm getting at is going to the left, this thing is going to get smaller and smaller, but it's never going to reach 0. So our graph kind of looks like half of a parabola, but not really in that, well, I mean, if you just look at the right part, but the left doesn't go up. It just keeps getting closer and closer to the x-axis. Well, let's talk about what's going on with this equation. First of all, do you see that it is a function? It passes the vertical line test.
Yes.
Correct.
Second of all, do you see that it is a one-to-one function because it passes the horizontal line test?
Yes.
Yes.
Okay. Now, it has a y-intercept at 1. It does not have any x-intercepts. What's the domain? The domain would be all real numbers. Do you see that?
Yes.
How about the range, though? So the domain is all real numbers, but the range would be greater than 0. Okay?
Yes.
All right with that?
Greater than 0 because it's, can you explain that one?
Okay, so let's go back over here with this table and let's extend it up in the negative direction, okay? So let's do this. Let's take -2 is here and -3 is here. This is an 1/8 and this is a 1/4, -4, -5, -6. This is going to be 1/16. This is going to be 1/32. This is going to be 1/64. You following?
Yes.
So eventually it's going to be 1 over a really big number, but 1 over a really big number is not 0. It's really close to 0, but it's not 0.
Okay, I see that.
Okay, good, good. All right, now, let's see here. I want to erase all of this. Let's take a look at the equation y equals 3 to the x power. Okay. Actually, there's one more thing I want to go back and say about that first equation. Do you notice that what's going on here with these y values is they're doubling as x increases by 1, y is doubling. Does that make sense?
Yes.
Yes.
So what do you think these are going to do?
Triple?
Triple.
Exactly. All right. So if when we use -3, -2, -1, 0, 1, 2, and 3, if y equals 3 to the -3 power, that's 1 over 3 cubed, that's 1 over 27. If x is -2, y equals 3 to the -2 power, which is 1 over 3 squared, which is 1/9. If x is 1, y equals 3 to the negative 1, which is 1 over 3 to the 1, which is 1/3. If x is 0, y equals 3 to the 0, which is what?
1.
1. If x is 1, y equals 3 to the 1, which is 3. 3 squared is 9, and 3 cubed is 27. So now these values are tripling because the base is a 3. So each time x increases by 1, you have an extra factor of a 3 that you're multiplying everything before by. So they triple. Graphing that, negative 3 is about right there, 1/27, 1/9, 1/3, 1, 3, 9. So this graph ultimately climbs steeper faster, doesn't it? But it still has a domain of all real numbers, has a range greater than 0. It has no x-intercept. It has a y-intercept. And oh yes, I forgot to say this about the previous graph as well as this one. We say that they are increasing over their entire domain. Starting at the left, going to the right, they're going up. Okay? Now, we're going to look at another one. And we'll be environmentally great. We'll go green. Let's take a look at y equals 1/2 to the x power. Okay? So x and y, -3, -2, -1, 0, 1, 2, and 3. Okay. Well, when the base was 2, it doubled. When the base was 3, it tripled. So what do you think is going to happen when the base is a half?
It'll cut in half.
It'll cut in half, absolutely. So it's going to get smaller. All right, if x is -3, y equals 1/2 to the -3 power would be 2 over 1 to the +3 power, which is 8. If x is -2, y equals 1/2 to the -2 power, which is 2 over 1 to the 2 power, which is 4. And I'm going to, let's see, y equals 1/2 to the -1 is 2 over 1 to the 1, which is 2, 1, a half, a fourth, and an eighth, respectively. Okay, you okay with that?
Yes.
Yes.
What does that look like? Well, let's see. When x is -3, y is 8. When x is -2, y is 4. When x is -1, y is 2, 0, 1, 1/2, a fourth, an eighth. Oh, that looks like the reflection of the black graph, y equals 2 to the x, doesn't it? Because instead of everything doubling, it's halving, so to speak, or halving. It still has a domain of all real numbers, a range greater than 0, a y-intercept of 1, no x-intercepts, but we say that it's decreasing over its entire domain. Okay? Questions?
No.
Okay.
No, I'm okay.
Right. Look at a couple more examples here. Let's see, let's go with blue. How about y equals 1 to the x? I did something larger than 1, 2, and 3. I did something between 0 and 1/2. Let's do 1 to the x. Let's see what we get there. So if y equals 1 to the -3 power, that's 1 over 1 cubed, which is 1 over 1, which is 1, right?
Yes.
If x is -2, y equals 1 to the -2, which is 1 over 1 to the 2, which is 1 over 1, which is 1, right?
Yes.
What's that going to look like?
Horizontal.
Yeah, so that doesn't fit the pattern. So basically we say that the base, this thing, cannot equal 1. because when it does, we don't get an exponential equation. Okay? One more example. Let's see, we'll go back to red here. Y equals -2 to the x power. Now, understand that is not the same as -2 to the x power. In this case, it's like 2 to the x, but then the negative comes after the fact. The 2 is the base, not the negative. But in the case that I want to look at, the base is -2. Okay? So again, let's make a table. And I'm just going to pick some nice values till you get the idea. 0, 1, 2, and 3. When x is 0, y equals -2 to the 0 power, which is 1. When x is 1, y equals -2 to the 1, which is -2. When x is 2, y equals -2 the quantity squared, which is +4. When x is 3, you get -2 cubed, which is -8. Now, what is that going to look like? Well, you've got 0, 1, and then 1, -2, and then 2, 4, and then 3, -8. And so that thing's bouncing all over the place. And those are just for specific values. What about all those values in between? You can't graph it. It doesn't work. So the conclusion from all of this is the following information. And this is what I wanted to get to here eventually. If we have an equation, or rather a function, right? These are functions, in the form y equals b to the x power. First of all, b cannot equal 1. B has to be greater than 0. Okay? If b is greater than 1, the graph increases over its entire domain. If b is less than 1 but greater than 0, the graph decreases over its entire domain. Any question about all that information?
Do you
Not
mind
so
repeating the last one, the very last one? I was writing down and I didn't hear it. I'm sorry.
Tell you what, I'll just go through the whole thing again. B can't equal 1, because when it does, you get that horizontal line. B has to be greater than 0, because otherwise you get dots and you just can't graph it. If b, and b is this base, is greater than 1, it's going to increase over its entire domain. If b is less than 1 but greater than 0, it's going to decrease over its entire domain. Did you get all that?
Yes, thank you.
You're welcome. Okay, now let's go back and talk about parabolas for a minute. And let's see, let's go to a new page. And if we had, and I'm just going to make some quick sketches that aren't going to be super accurate. I just want to get the point across. If we have y equals x squared, we've got this thing that looks like that and goes through the origin, right? If we got y equals x squared plus 3, now instead it is up 3 units, right? If we've got y equals x squared minus 4, it's down 4 units. Okay? You remember all that from parabolas?
Yes.
All right, now, let's say we've got, let's say we've got y equals 2 to the x power, and that graph looks like that, okay, very roughly. What do you think y equals 2 to the x plus 3 is going to look like?
Would it be up 3 units?
Exactly. So it's going to look just like this, up 3 units. So instead of it having a y-intercept at 1, it would have a y-intercept at 4, and then it's going to look, again, I'm not making super accurate graphs. I'm just trying to get you the general idea. What about y equals 2 to the x minus 5? What would that look like?
Down 5 units.
Right. So instead of your intercept being at 1, 1, 2, 3, 4, it would be at negative 4. Okay, because it would be down 5 units. Okay.
Yes.
All right. Now, let's go back to our parabolas. Y equals x plus 2, the quantity squared. Well, wait. That's not what I wanted to do. Sorry. Okay. Y equals x squared. I want to start there. Looks like that. What about y equals x plus 2 squared? What does that look like? Remember, if it's on the inside, inverse, it goes 2 units to the left.
Oh, yeah, that's right. I forgot.
Okay. And y equals x minus 4 squared would go, what, 4 units to the right?
Yes.
Yeah.
Okay. Don't you just love my drawings? They're just wonderful, aren't they? Yeah, right. Okay, now, y equals 2 to the x. Looks like that. Y equals 2 to the x plus 1. Now, that's not this. This, the 1 is a constant out separate. It moves the graph up 1 unit. This one is part of the exponent, so it's locked up in there with the variable. So that moves the graph to the left 1 unit. Okay? And y equals 2 to the x minus 4 would move the graph to the right 4 units. You follow?
Yes.
Okay.
Yes.
What do you think this would look like? Oops, let's hang on. Tried to go too fast here again. If y equals 2 to the x looks like that, what about y equals negative 2 to the x? What would that look like? Okay.
Would it be the opposite because it's technically, since it's not in a parentheses, a negative just follows, right?
Right? Yeah, so all your y values would be opposites. So your graph would look like this.
I don't remember the proper term, the one that we went over yesterday. Inversely? No, I don't know.
No, it's not the inverse.
Symmetry, something symmetry. No. We went over it yesterday.
Well, we talked about a one-to-one function and its inverse would be symmetric about the line y equals x. Okay, but these aren't inverses.
They're not. Okay.
No. The inverse of this is a log function. That's coming later. I think that comes Monday. Yes, that's coming up.
Oh, no. Okay.
Yeah. So these are just, your y values are going to be the opposite of the y values over here. So your graph is going to open down like that. Okay.
Alrighty.
All right. Another point I want to talk about. If you took this and rewrote it, getting rid of the negative exponent, wouldn't it be this?
Yes.
Yes.
So this is a decreasing function, just like that. Even though the base is larger than 1, because the exponent is negative, it ends up ultimately looking like that. So then it's decreasing, whereas this is an increasing function. So this one increases, this one decreases. This one is just like this one, it decreases. Okay.
Okay.
All right. Now, I'm going to look at some applications. And I guess we can just stay with this screen. And we'll go to the white screen. Okay. Here is an equation. Now, it says A equals 500 times 2/3 to the t power. This is the exponential part of the equation. This would be the starting amount. Why? Well, let's say that t is time. At the beginning of time for this problem, t would be what? At the very beginning.
Would it be 1?
No. You're
2/3.
no. T would be 0. Have any of you ever run a race?
Yes.
No.
Okay. No, never run a race. Not even as a kid on the playground.
Yes, like
Okay.
years ago.
Well, that's fine. Years ago is okay. 2 or 3 years at least, right? Okay. You're standing at the starting gate and the guy puts the gun up to fire it to start the race. Okay. Before he fires the gun, you're standing there. How much time has it taken you to run this far?
0.
Right. At the beginning, t is 0. Well, if t is 0, what's 2/3 to the 0 power?
1?
What's 1 times 500?
500.
Right. So 500 is the starting value. Okay. What does the fact that the base is 2/3 tell us is going to happen to that starting value as time goes on? Is it going to get larger or smaller?
It's going to get larger.
Mm,
No? Because it increases over time.
Base is between 0 and 1.
Oh, smaller. It's going to decrease.
Right.
If
Because
it's greater than 1, then that's when it increases.
bingo. Okay. So what have I got? I've got a population that starts out at 500 and it's decreasing. Now let me actually read you the problem. It says 500 grams of a radioactive material decays according to the formula. Okay. So there's the 500 grams and there it is decaying because the base is less than 1. You all right with that?
Yes.
Find the amount present in 10 years. So they want us to find, if we were to use function notation, they want us to find a of 10. Okay. It says round to the nearest 1/10 of a gram. So we're going to put that in our calculators. We've got 500 parentheses 2 divided by 3 close parentheses raised to the 10th power. And I'm getting 8.67076 blah, blah, blah. And it said round to the nearest 10th. So the 6 is in the 10th column. The 7 would round up. So approximately 8.7 grams is what's left. So we started out with 500 grams of a radioactive material. 10 years later, there were only 8.7 grams. You okay with that?
Yes.
Yes.
It's the reason I wanted to ask you those questions before I read the problem is to show you that you can figure out some things like what's the starting amount? Is it going to increase or decrease? That kind of stuff. Okay. New example. Population growth. P equals 3, 745 parentheses 0.93 to the t power. Here, t stands for time in years, and p stands for the population of a given place, okay? And in fact, it's called the population of North Rivers. What's the beginning population at the beginning of time? What's the population?
3,745.
Good. Is the population increasing or decreasing?
Decreasing?
Decreasing.
Right. Now be careful of this next question. At what percentage rate is the population decreasing? Careful.
Would it be 9.3?
No, no,
93%?
no,
Doesn't it start decreasing at the beginning?
yes,
So 1,
no.
0.
Okay, here's the thing. 0.93, that is 93%, but that's what's happening as time goes on. Each time t goes up by 1, you multiply what was there by 93%. So you have 93% of what you had. So what are you losing?
7%?
Bingo.
How'd you get 7?
100 minus 93.
Yeah.
Oh, I
You
was
see
like,
it now?
7 come from? Okay, yeah, I see
Oh,
it.
yeah, it was going to be tricky. I warned you. So we're losing 7% because each time we're keeping 93% of what we had. Okay?
Yeah.
Right, I got it now.
Okay, now let me read the problem. The population of North Rivers is decreasing exponentially according to this formula, where t is measured in years from the present date. Now, find the population in 6 years, 9 months. Now be careful. T stands for the number of years. So P of what? Again, be careful. How would you describe 6 years, 9 months in terms of years?
Would you do 6 and 2, or hold on. Are you gonna do a decimal or a fraction?
We can do it either way. We'll start with fraction if you want, and then we'll change it to a decimal. So what fraction of a year is 9 months?
3/4.
Okay, wouldn't that just be 6.75?
Yeah.
Okay. So we're going to take 3,745 times 0.93 raised to the 6.75 power, and we get 2,294.62. And since we're talking about population, we'll round to the nearest person. The 6 would round up, so 2,295 people. Okay? All right with that?
Yes.
Okay. Now, we're going to look at a formula that is used for compound interest. P is the principal. I always have to stop and think, is it spelled A-L or L-E? I think it's A-L for this. I'm trying to look and see if I can find it. Oh, well, we'll just hope it's right. Yes, it's right. I found it. Okay. R is the annual interest rate. K is the number of compoundings per year, and T is the number of years. and A is the ending amount. Or I like to say accumulating amount just because of the A. But anyway, okay. Now, if interest is compounded once a year, K is 1. If it's compounded semi-annually, K is 2. If it's compounded quarterly, K is 4. If it's compounded monthly, I can't hold up 12 fingers, but K would be 12. Okay?
Yes.
All right. So using this formula, let's take a look at some problems. Let's see, hang on. Let me go back and undo that, and then we'll erase all of this. And let me get the scenario. It says an initial deposit of $10,000 earns 8% interest, compounded quarterly. How much will be in the account after 10 years? Okay, so we're investing $10,000 at 8% annually. Interest is compounded quarterly, and we're going to leave it there for 10 years. How much money will we have at the end? Any questions before we go on?
No.
No.
All right, so A equals 10,000 times 1 plus 0.08 over 4 raised to the 4 times 10 power. Now, I could put that all in my calculator at once, or I can do some simplifications first. For instance, I could take 0.08 divided by 4 and get 0.02. I could take 4 times 10 and get 40. And so I could, simplify it first. If you do that, that's fine as long as they give you exact answers. Don't round off. So like if this number doesn't come out to a nice exact answer, you just need to leave it as it is and don't do any rounding till the very end. Okay? I'm just going to leave it as it is for now. So in my calculator, I'm going to go 10,000 parentheses 1 plus 0.08 divided by 4. Then I'm going to close the parentheses. Okay. Use my little power caret. Parentheses 4 times 10. Okay. So again, this is what I put in there. I put 10,000 parentheses 1 plus 0.08 divided by 4. And then I closed it up and I used the little caret key, 4 times 10. Now, if I'm going to have a product up there, I need to put them in parentheses. But if I'm going to make it into just a 40, then I could just write 40. You follow what I'm saying? But if you got more than one.
Sorry, either way you put it in, you'll get the same answer, right?
Yeah.
Okay.
To me, this is quicker. You don't simplify anything first, but you also need to make sure you put all your grouping symbols and everything in there. Okay. I'm getting 22,080.39664. And so rounding to the nearest cent, the 6 would round up, we'd get $22,080.40. All right with that?
Yes.
Okay.
I'm not getting that answer. I don't know. I tried it like 3 times and I keep getting the same answer.
Okay.
So I put 10,000 parenthesis 1 plus 0.08 divided by 4, close the parentheses, caret 4 times 10.
You're not putting parentheses around the 4 times 10.
Oh, okay.
So what it thinks you're doing is you're taking it raised to the 4th power, and then that result times 10. So you need to suck that 10 into the exponent.
I see. There we go. I got the correct answer.
You need that exponent sucker.
Okay.
Whatever.
Thank you.
You're welcome. Sorry, I'm getting carried away. It must be Friday. I probably should be carried away by some people, but that's another story. All right, let's go on to another example. This says, comparing interest rates. How much more interest could $1,000 earn in 5 years compounded quarterly than the annual interest rate of 5.5% instead of 5%? Okay, so for, let's see, P is $1,000 in both cases. The time is 5 years in both cases. The first one says compounded quarterly as opposed to, let's see. Oh, wait. They're both compounded quarterly. Okay, sorry. The only thing that's different is the interest rate. So the first interest rate, it's 5.5%. So that would be 0.055. And the second one is just 5%. So that would be 0.05. Okay, so in both cases, we're investing $1,000 for 5 years, compounded quarterly. But the first case, the interest rate is 5.5%. The second case, the interest rate is 5%. Okay. You know where people mess up the most? Converting the percent into a decimal. So be careful with that. We're going to use this formula. A equals P times 1 plus R over K to the KT power. So this is going to be A equals 1,000 times 1 plus 0.055 over 4 raised to the 4 times 5 power. Okay, so 1,000 parentheses 1 plus 0.055 divided by 4, close it up, raised to the parentheses 4 times 5 power. And if you want to take 4 times 5 and make it 20 and save having to put parentheses around the exponent, no problem, either way. 1314.066. So the 6 in the 1/10 of a cent column would round up. So you'd get $1,314.07. Okay. Now we're going to do the same thing, but with a 5% interest rate. So 1,000, 1 plus 0.05 over 4 to the 4 times 5 power. And here I get 1282.037. So 1282.04. And let's see, what's the difference between those? 1314.07 minus 1282.04, $32.03. So same amount of money, same amount of time, same amount of compoundings, but by having a 0.5% more interest rate, you'd get $32.03 more. Does that make sense? Better interest rate,
Yes.
more money you make. Okay, one more problem, and then we'll turn you loose for the weekend. Compound interest. If $1 had been invested on July 4th, 1776, at 5% interest, compounded annually, what would it be worth July 4th, 2076? Okay, so we're going to invest $1. The interest rate is 5%. It's compounded annually. 1776 to 2076 would be 300 years. Okay? So A equals P times 1 plus R over K raised to the K times T power. Let's simplify this first. What's 0.05 divided by 1? 0.05, right?
Yeah,
Yes.
What's 1 times 300?
300.
100.
What's 1 plus 0.05?
1.54.
Yeah. And in fact, I can drop that 1, can't I? Because when I get the answer for that and I take it times 1, I'm going to get the answer. So basically 1.05 to the 300th power. See what you get. 1.05 to the 300th power. I'm getting 2273996.129, which is 2273996.13. $2,273,996.13. Just think if Ben Franklin had been your great-great-great-great-great-grandfather or something and had invested $1 in a bank that was still there, but yeah, anyway. All right with that?
Yes.
Okay, so over the weekend, you've got section 11.3. I'll be back at 1:15 with my office hour. Otherwise, have a great weekend, and I will see you all on Monday.
Thank you.
Have a great weekend.
Thank you.
You too.